All right, welcome back. Now we're going to put all that we've been doing, we're going to put that all together in our procedures for curve sketching. This should be on page 193 or so of your workbook, depending on which version of the workbook you have. And so let's go ahead with this. It's going to take all that we've been doing in the last few sections and let's going to mash it all together. Let's see how we can make ourselves a graph without a graphing calculator. I know that in the notes and in the practice questions, or in the last section, there were some graphs that we were putting together in there, but let's just start to formalize this process and add all of it together. Let's first start to look at determining what your domain of your function is, listing your zeros, so your x-intercepts, find your y-intercepts. We should also determine any symmetry. That's the whole thing about even and odd functions, and we will look at that to see if that is relevant for our graph. Asymptotes, so we will look at not just vertical asymptotes, which are fairly straightforward to get to, but we'll look at also horizontal and oblique asymptotes if needed. Number 4, first derivative test. We look at to see where it's increasing, where it's decreasing by taking your first derivative, finding where it's positive or negative. Using first and second derivative tests to find your relative extrema, noting your max and your min. That will be a big help in starting to put together this graph. And then number 6, using your second derivative test that we did in the last section to figure out where it is concave up, concave down, points of inflection, and then all of that together we will now use to sketch our graph. Let's start off with f of x is x squared minus 1. We start off by saying, all right, so this is x plus 1, x minus 1, over x plus 2, x minus 2. Of course, that is relevant for our domain. Our domain is the set of x's such that x can't be plus or minus 2, but anything else is good. All right, so here's step 1. Step 2, if we're looking at our zeros, we're seeing where our function is equal to. What values of x will make this equal to 0? That will happen when x is plus or minus 1. So therefore, we have negative 1 comma 0, we have 1 comma 0, and we have about a y-intercept. If you let x equal 0, this becomes negative 1 over negative 4. So just 0 comma 1/4. Pretty straightforward, no big deal. All right. Now this ramps up a little bit, and we're going to look at our asymptotes. Right? We know that we have a limit as x goes to infinity. If we're going to go off to the right, what happens to x squared minus 1 over x squared minus 4 back into our original form? We're going to divide top and bottom by x squared. By doing this, this will equal the limit as x goes to infinity, 1 minus 1 over x squared divided by 1 minus 4 over x squared. So this is equal to 1. Therefore, we have a horizontal asymptote when y is 1. We do know we have vertical asymptotes at x is plus or minus 2. And because we have a horizontal asymptote, we don't have oblique asymptotes, of course. Next, let's look at our first derivative, f prime of x. It's equal to 2x is your derivative of f, derivative of the numerator, I should say, times x squared minus 4 minus x squared minus 1. And derivative of the denominator is 2x all of this divided by x squared minus 4 squared. All right, let's see how this tidies up. 2x times x squared minus 2x times x squared, that's all just going to subtract away. What we're going to be left with in our numerator is 2x if we, or we could factor this either way. We should end up with negative 6x. We should have negative 8x minus negative 2x. Gives us negative 6x. If we want to do that by factoring and common factor out 2x, and then we're left with negative 3 in our square brackets either way. And this ends up being over x squared minus 4 all squared. And this is our f prime of x. So I'm running out of room, so let's draw a vertical line and continue up here. We have critical numbers that we can see from there. Anything that makes the denominator equal to 0, so plus or minus 2. The numerator is 0 when x is 0. So those are our critical numbers. Let's draw our number line, negative 2, 0, and 2. And we're going to look at those three zones. When x is negative 3, something in that left, this ends up being negative 6 times negative 3 is positive. And then what we're going to have down here, no matter what, x squared, we're going to square it, we're going to subtract 4, and then we're going to square that again. So the denominator will always be positive. So it's just negative 6 times x is the numerator is going to be positive and negative. So here we have, here we have positive values in this interval. When x is negative 1, negative 6 times negative 1, it's going to be positive. The denominator is still always positive. When x is 1, negative 6 times 1, so the numerator will be negative. And then negative 6 times a number greater than 2 makes that negative. Therefore, it is increasing. On negative infinity to negative 2, union negative 2 to 0. Now, why do I have to break that into two intervals? Remember that we've got a vertical asymptote at negative 2. So it's going to be increasing to an asymptote and then increasing after the asymptote. It's perhaps going to look something like this. That kind of, it tells me that it's going to be increasing to negative 2, and then right of negative 2, it's going to be increasing again. We've got that vertical asymptote, so that's going to be the case. That's what it's going to end up looking like. So there's my increasing zone. It is decreasing, same sort of thing. We need to break this into two intervals of decrease, decreasing from 0 to 2, union decreasing from 2 to positive infinity. We have a relative max where it changes from positive to negative slope. The relative max at 0, 1/4, which we've already found to be our y-intercept. So there's our next piece. Second derivative. Second derivative, f double prime of x. Our first derivative was negative 6x over x squared minus 4 all squared. So this will equal to negative 6. There's your numerator derivative. Denominator stays the same, x squared minus 4 all squared. We're going to subtract Negative 6x is your numerator. Derivative of your denominator. Now we need to chain rule this. So this ends up being 2 bracket x squared minus 4 all to the 1 times the derivative of the inside. Don't forget. Derivative of the inside is 2x. And this is all divided by the denominator. X squared minus 4 squared squared. So x squared minus 4 to the 4. We can now clean this up a bunch. I'm going to common factor out negative 6 from each of these. I'm going to common factor out in this. In the first half, we don't have any x's, so we're going to leave that. But x squared minus 4's, we have at least one factor that in each of the front and the back half. And that's going to be it. That's what all I'm going to common factor out. Leaves me behind with, in the front half, just 1 of x squared minus 4. In the back half, what does this leave us behind with? We've got a bunch of different pieces. We've common factored out 6, but we're leaving behind that x, and that 2, and that 2, and that x, and that should be it. And so we multiply that together, gives us minus 4x squared. Close our square brackets. What do we have downstairs? We have x squared minus 4 all to the 4. All right, what can we do to tidy this up? Negative 6. This x squared minus 4 is going to divide out with one of those. So it's minus 6 leaves us with, let's probably common factor a negative 1 out of that square bracket, right? So let's call this positive 6. Leaves me with, what do we have here? That's negative 3x squared in the square brackets. So we common factor out negative. This ends up being 3x squared plus 4. We've common factored out that negative. What do we have left downstairs? X squared minus 4 all cubed. So this is our second derivative. We still have possible POI when x is plus or minus 2. Please take note that this will never equal 0. 3x squared plus 4, because you're squaring x, which makes it positive, times 3, and then we're adding 4. That is never going to equal 0. And so therefore, we look at double prime of x. Looks like this as a number line. Here's negative 2, here's positive 2. We have left of negative 2. What does this look like? This looks like 6, which is positive. This 3x squared plus 4, which is always positive. And then we have x squared minus 4 all cubed. X squared minus 4, if we are over in this zone here, we are looking at negative 3, say. Negative 3 squared is 9, subtract 4, which is 5. We cube it, that's going to be positive. And this ends up being positive in this zone. Between this, between negative 2 and 2, say a number like 0 makes this positive, divided by 0 minus 4 is negative 4 cubed is negative. So in between we have negative, and then this ends up being positive out here when x is greater than 2. So what that tells us our concavity. That tells us that this is concave up, tells us this is concave down, tells us this is concave up. We can kind of amend that to our number line too. Back when we did first derivative, we could say, okay, so this tells us that this is increasing, increasing, decreasing, decreasing. You see that some people doing that just as a visual note for what's going on here. All of that together, I'm going to move to the next page just because I'm starting to run out of room. Points of inflection. where our concavity changes from positive to negative or negative to positive. That happens at -2 and it happens at +2, but we have to be careful in here because those are vertical asymptotes. Those are not defined in our function, and so we have no points of inflection because f little prime of x is never equal 0. And if we put all of this together, so let's do a nice little sketch of this. All of these things put together, we know we've got vertical asymptotes at ±2. We know that from our domain. We have x-intercepts at -1, 0, and at +1, 0. Then x-intercepts. We have a y-intercept at 0, 1/4, which we know is a relative maximum. We know we have a horizontal asymptote, y equals 1. We know that it is increasing from -∞ to -2. We know that it is increasing from -2 to 0, and it is concave down. And then from 0 to 2, it is now decreasing, but it's still concave down. And it looks like this. And our last piece is when x is greater than 2, it is decreasing, and it is concave up. And it looks like this. So there's our function altogether. We've got our maximum in there. We've got a relative maximum. There's no absolute maximum or absolute minimum. We also don't say that there's a relative, this is an interesting question. We also don't have a relative minimum here because it is always decreasing as x goes to infinity. It is getting closer and closer to a height of 1, but it's never going to reach that height of 1. So we don't have a relative minimum there. It's an asymptote, so be careful about that. All right. Given the graph of f prime, describe and sketch the graph of the function of f. Let me zoom out of here a little bit, maybe. Describe and sketch the graph of our original function. Okay, so in this question, given the graph of f prime, describe and sketch the graph of the original function. So this is our first derivative graph. This is measuring the slope of our original graph. And so what that tells us is that at a, we have our first derivative is equal to 0. That tells us that our original graph is going to be flat there. It's going to be horizontal. Our first derivative graph is negative, right? This is down here. So we have a negative slope, and then we have a positive slope. And so if we have a negative slope turning into a positive slope, what does that mean on our original graph? It means we have a minimum. So let's start to list this. So we have a minimum at A. We also have at E. At E, we have a slope of 0. And left of E, we have a negative slope, and right of E, we have a positive slope. So negative and then 0 and then positive slope means we have a minimum at E also. So we have a minimum at A and at E. What else is going on here? What's going on at C? Same thing. We have a slope of 0 at C. We have a slope of 0 at C, but it's moving from a positive slope to a negative slope. So positive slope to a negative slope means we have a maximum at C. What else do we have going on here? At B, our first derivative, has a flat point, which means the slope of our first derivative is 0, which means the second derivative at B is 0. So at B, what do we have? We have an inflection point. We have an inflection point because our first derivative it's going from increasing to decreasing, which means our second derivative is going to go from positive to negative. It's going to go through that point there, and we have an inflection point at B, and then the same thing at D and D. So we have an inflection point at D on our original graph, right? Because our first derivative is flat at D, which means our second derivative will be 0 at D. So putting all of that together, it is increasing from A to C because our first derivative is positive. It's also increasing from E to infinity because our first derivative is positive. It's above. It's above, so therefore that means it's a positive slope. Where is it decreasing? It is decreasing. The graph is decreasing elsewhere. It is decreasing where we have a negative slope, so negative infinity to A. And it's also decreasing, we have a negative slope from C to E. All of this together means our original graph is going to look like this. It is decreasing until we get to A because our first derivative is negative. From A to B, it is now increasing because it has a positive slope. From B to C, it is still increasing, but because our first derivative is decreasing, that means it's now changed to convex down, or concave down, sorry. After C, what's going on from C? It now starts decreasing because my first derivative is negative. At D, it changes concavity and it changes to concave up. And it is now increasing. From E to infinity, it's increasing. And that should do it. Number 3, last one. Sketch the graph of x cubed minus 3x squared plus 4. All right, so let's look at all these pieces together. Our first thing is, so our domain is all real numbers. Because it's just polynomial. We want to try to factor this. So we look at candidates to be able to factor this. Factors of 4 plus or minus 1, plus or minus 2, plus or minus 4. So we could plug in here and we can find pretty quickly that f at negative 1 is negative 1 cubed minus 3 times 1 plus 4 ends up being 0. Therefore, negative 1, and then we have 1x cubed, we have minus 3x squared. We have no x term, so we need a 0 there, and then 4. We do our synthetic division, bring your 1 down, multiply negative 1 times 1 is negative 1, add down is negative 4, multiply, add down multiply, add down. And that better be 0, because that's how this is set up. So therefore, what can we conclude? Therefore, f of x is equal to x plus 1 is what we've factored out. And what does it leave us behind with? It leaves us behind with x squared minus 4x plus 4, which we know is x plus 1 times x minus 2 squared. So we have x-intercepts of -1, 0. We've got 2, 0. We have a y-intercept of 0, 4. All right. Moving on. First derivative. F prime of x is equal to 3x squared minus 6x. We factor that, it ends up being 3x bracket x minus 2. And if we have 0 equal 3x, x minus 2, we have critical numbers. Of x equals 0 and 2. All right. So f prime, there's 0, there's 2. We look at these factors, and when x is less than 0, this ends up being negative times negative, x is positive. Between 0 and 2, it ends up being positive times negative. And between, so greater than 2, this ends up being positive times positive. So this is increasing, and then it's decreasing, and then it's increasing. We do need to state what those zones are: increasing on -infinity to 0, union 2 to infinity, decreasing in between 0 to 2. Therefore, we have a relative maximum when we're increasing and then decreasing. So we have a relative maximum at 0, 4. We have a relative minimum at 2, 0. All right, second derivative. Second derivative, if our first derivative is 3x squared minus 6x, then we have 6x minus 6, which is 6 bracket x minus 1. And if we let 0 equal 6 times x minus 1, and therefore x equals 1 is a possible point of inflection. We have a possible point of inflection at 1. So we draw a number line. Here's 1. What is it doing to the left and to the right? Left of 1. So when x is 0, this becomes negative. And then greater than 1, if x is 2, this is positive. So this is concave down. And then it is concave up. Therefore, we have inflection point because we change concavity, and it's defined at 1. So therefore, an inflection point at 1, comma, we plug that into our original function, it ends up being 1, 2. All right. Now, all of that thrown together, what does this look like? Okay, so all of that put together. We have -1, 0 is one of our x-intercepts. 2, 0 is an x-intercept. We know from Math 30-1 that it has a multiplicity of 2, so it's just going to touch the x-axis at a tangent there. We have 0, 4 is a, not only is it our y-intercept, but it's also a maximum there. So we have a relative maximum at 0, 4 at our y-intercept. And so this is increasing from -infinity to 0. It's increasing into here, and it's decreasing from 0 to 2. But one of the important piece to this, it is decreasing at 1, 2. We've got a inflection point, and it changes right here. It changes from concave down to concave up. And so we want to graph that on there as well. And that is what it looks like. Thanks so much. Good luck.